So we're going to start. Maybe there's someone still missing, but we're already 18 people, so we're going to start. Je voudrais commencer en français parce que je sais qu'il y a beaucoup de gens qui parlent français. Alors, bienvenue. Je vais me présenter. Je suis Jaume Nin, le PDG adjoint à TMCOMAS, avec mon frère, Llorenç, et notre père, Llorenç Senior, qui est le PDG. Je suis très contente de vous présenter cet webinaire, le premier en anglais, et j'espère que nous en ferons beaucoup plus. Qui va faire le webinaire, c'est le PhD Jaume Nin, notre chef du département de recherche technique, développement et innovation technologique. Au fan aussi, il y aura Olga Ivanushina de notre équipe commerciale qui fera la fermeture du webinaire. Donc, je vous laisse avec Jaume et j'espère que vous apprécierez le webinaire. À bientôt et prenez soin de vous. Now in English. So welcome. I'm Jaume Nin, Deputy CEO here in TMCOMAS, together with my brother, Llorenç Jr., and of course with our father, Llorenç Senior, who's the CEO, the big boss. I'm so happy to introduce you all to this first webinar we're doing in English, technical webinar, and I hope we'll do much more. PhD Jaume Nin, he's going to do this webinar today, and he's the head of our technical research, development, and technological innovation department. And also at the end, Olga Ivanushina will close the webinar. She's a sales engineer from our sales team. So I leave you with Jaume, and I hope you enjoy this webinar. See you soon, and take care. Jaume, your turn.
Thank you, Georgina. Bonjour à tous. Good morning, good afternoon, everyone. The webinar will be in English, and hopefully all of you will follow me. If there is something that you don't understand, if you have some questions, you have the option to stop me by raising the hand or by asking your question in the chat, or just at the end you will have some questions and answers time for all of you. Let me present myself. I am the technical director for TMCOMAS, and I am in this position since 12 years. So I have quite a lot of background in repairs and in different machining procedures in the workshop. My original background is chemical, so I am a chemist. After I make my PhD in material science, and especially in thermal spray coatings in the University of Barcelona. And then I made also the welding engineering master. So I am also a welding engineer, international welding engineer. I am also quite active in brazing, heat treatment, material science in general, and so on. So I am more or less quite an expert in material science, and especially in the use of different materials and how to treat different materials to help our customers in their repairs on their new parts, as I will explain. Let me start with my presentation, and hopefully you will like it a lot. Let me check if I'm able to. Okay, here it goes. Okay, so if everything is okay, you will be seeing right now the first slide in this presentation. The title is Surface Technologies as a Solution to Meet Industrial Needs. Okay, this first webinar is quite, I would not say basic, but introductory to surface engineering technologies. There are plenty of them. I don't want to explain all of them to you. I just wanted to highlight some of them, pointing out to the technology that we have here in house. And well, it's a basic talk, so don't get disappointed if that webinar is not meeting your demands. We can perform some of them more technical, complex. So okay, here it goes. First, we will be introducing what is surface engineering. It's quite a brief explanation. Then the best technology selection criteria that I am using day by day. After surface modification technologies, conclusions, and questions and answers. So by surface engineering, it's a quite ample definition, but I like to use that words to explain that all the techniques that are helping us to modify a surface of a material. For what purpose? To enhance the properties, to increase the hardness, to increase the corrosion resistance, whatever. But it has a clear object that to modify the surface. So there are two big ways to do that, more or less. So one is to do by modification of the material structure. All of you know that once you modify the structure of a material, you will modify the property of that material. By changing the structure, you can change some properties. The key point is to know which structure you have to change, or in which extension to increase one property or another. And this example is a clear example of a diffusion surface treatment. Here in the left side of the picture, you can see that area, that white coating, white layer, is a diffuse layer, and then here is the base material, the substrate material, which has not been affected by this surface modification. So in this picture of a nitrating process, this is 20 microns, so about 20 microns of the surface has been modified. After that, the substrate is more or less non-affected, non-modified. In the other hand, we can also apply a coating completely different of the base material, and with a lot of different techniques to apply these coatings. But these coatings will be acting in a different way because it's completely different material than base material. So in this case, for example, is a laser cladding of spherical tungsten carbide. Here you can see all the tungsten carbide spheres here in a matrix of nickel alloy made by laser cladding. So this picture clearly shows us that this surface of this bulk material is not anymore made of this base material, but of tungsten carbide layer. So the hardness and the wear properties will be completely different. Another example, in this case, is a thermal barrier coating. In this case, is produced by the use of two different technologies. Here we can use, for example, a thermal spray coating of a nickel base alloy or M-Crally, and then a top coat by, for example, PVD or electron beam, or thermal spray of, in this case, ETIA stabilized zirconium. So this is a 2 layers coating that will act as a thermal barrier for this inconel substrate to protect the inconel substrate of the heat of the combustion chambers in some blades or some turbine components, for example. So basically, there's 2 ways to modify the surface: by modifying the top surface in the bulk material, or by using a coating of a very different material on top. Okay, so during my daily work, a big part of this work is to help customers in problems. So, for example, in this case, I'm going to talk about the best technology criteria. So the first one is the location. Okay. So is this part that we have to repair? It can be moved. It can be moved. It can be removed from the workshop. It can be removed from the place that it is. Okay, then we have to decide if that reparation have to be done in the workshop or on site, or we can move this part to our workshop, or we have to work in on site. It's clear in this, for example, here we have a turbine, a very big turbine, and we are making, or someone is performing a heat treatment on site, clearly with all these thermal blankets to control the temperature and the heat treatment on this area. On the other hand, for example, in this big ingot, we have enough space in an oven, or the part is not finished, or the part can be moved to that big oven to make the heat treatment. Sorry. So the dimensions are quite important for as criteria. Also, the tolerance of the part to be repaired. So it's not the same if the part is in raw condition or if the part is already finished with tolerances. If the part is in raw condition, like this one, it means that it has no tolerances, or tolerances are very big. So we can use very aggressive heat treatments if it's needed. On the other hand, if the part is already finished, like this blade or this turbine blades in this turbine, multi-stage turbine, it's clear that the dimensions are finished. So we are going to need different techniques that are not going to cause a deformation or a big alteration in shapes, because we can spoil the parts. So another criteria is important is the state of the part. Is a reparation? Is a new part? Okay. Other criteria is not less important, is that user specification. Sometimes our customers are always worried about the harness because they have a wear problem, so they are very concerned on the harness. It has to be very hard. It has to be very hard. Okay, the harness it can be quantified. It's very popular. Everyone knows more or less what is harness, but it can be complex because there are a lot of conversions, a lot of different lectures, Vickers, Brinell, Rockwell C, Rockwell B. So we have to all speak in the same language. Sometimes it's difficult to explain a customer that he wants a coating or a layer that it's more than 65 Rockwell C. And then we are okay. I will apply you a coating that is 1,000 Vickers. Okay, but 1,000 Vickers, how many Rockwells is? Okay, it is not comparable. Maybe 70, but it's not comparable at all. So sometimes it's difficult or it's tricky to understand what the customer wants. Also about the thickness. Thickness is quantifiable, so you can measure the thickness by different techniques, by ultrasound, by eddy currents, by a simple caliper. So you can measure the thickness of your surface modification. But also the customers may ask for very, very thick coatings. Okay, not all the techniques are able to apply a very thick coating. Some of them, I will talk about it later. Some of the techniques are only producing coatings or layers that are very thin, and others can produce very thick layers. So thickness is also a criteria to have in mind. Wear resistance and chemical resistance. These are the key in our business. Very important, but difficult to assess because there are a lot of factors that can modify the weld resistance and the chemical resistance of a material once it is in place, once it is working. So it's always good to know as much as information as possible about the working conditions, the environment, the temperature. It's very important for us, or for me, to understand what is the problem on this part. Why is this part failing? Is it failing by corrosion? Is it failing by erosion? By temperature? By oxidation? So then I am always asking the customers that I have the opportunity to about the working conditions. Other specification can be some restricted chemical compounds. For example, some customers from the industry, from the food industry, are asking always if the coatings are complying with the FDA rules, or if they contain chromium 6. And sometimes our answers have to be, okay, if you want the hardness, the maximum hardness or the maximum weld resistance, it cannot comply with FDA. If we have to comply with FDA, you only have these two options. And it's clear that everything is not possible. And in some cases, our customers or the applications is very restricted for this because of these specifications. Other different specifications that the customers may ask is, for example, roughness, color, the electric properties in case of aluminum oxide thermal spray coatings, for example, and so on. Also, there are other criteria not less important. For example, the urgency or the criticality of the part. Some customers, as I said, may need some reliable, proven and approved processes, certified according to norms and regulations such as aeronautical, IPA, or UH in case of shipyards. No? In these cases, there are not a lot of choices. There are not a lot of surface technologies that can be applied, but only the ones that are allowed for these standards and regulations. Is the process qualifiable? It's a question that a lot of customers are making us when we are talking about laser cladding, because as a welding technology, they are used to have standard and qualified welding processes like in electrode or MIG or submerged arc welding. So yes, it's a question that everyone is asking for very critical applications, and the answer can be sometimes no. It's not a qualifiable process like a welding. It's a painting. It's a electroless, nickel, or whatever. So it's not qualifiable. Or sometimes it can be yes. It's a laser cladding, so we can qualify perfectly as another welding procedure. Depends also on the budget or price. Is the solution cost effective? Sometimes, depending on the price of the part, it's not worth to make it a big effort in repairing or in improving the properties of the surface. Trying to increase the life of the part is more convenient to change it or to replace it. But in most of the cases where our customers ask us, it's because they know that this part is not available in stock in the moment, or is very expensive. So it has a lot of sense to repair it. And then in this case, we are the right partners to do that. And last but not least, it depends on the responsible person. So it depends on the customer. How willing is she or he to test new innovative solutions? How tight it is by their bosses or by their company. In some companies, they are quite free to try new things, new coatings, while in other ones, they are quite restricted to what the technical department says or something like that. No? So in these cases, we have to play, we have to educate all these customers in the good things of our technicals, or in the good things of our reparations. Also, if it's an urgent repair, even if it has to be a part under a lot of specifications, in some cases the customer is more flexible because he or she is under in an urgency. So this is also a criteria to decide whether to use one technique or the other. Well, once I have explained you all these more or less which criteria we are taking into account to focus to try to address in a particular case, I would like to explain maybe 8 or 10 modification surface technologies. I have distributed them into groups. All these, or some of them that affects on the bulk of the material, can be conventional heat treatment, cryogenic heat treatment to increase maybe 1 or 2 Rockwell C in some knives for high-speed steel, for example. Cold forming, hot forming, as you can see here, we are forging a piece, we are forging a blade, and a compressor shaft, for example, or whatever. So to increase the toughness, to increase the impact values of this material by affecting all the bulk of the material. While in the other cases, in the other group, we have the technologies that affect on the surface. It will be conventional heat treatment like treating or case hardening, induction or laser hardening, organic or paints, coatings, weldings, thermal spray coatings, PVD and CVD, electrolytic processes, platings, chemical processes like electroless nickel, for example, and others. So let's have a look on them more or less. Okay, the first one is quenching and tempering. Quenching and tempering, all of you know what is quenching and tempering heat treatment. It's a very old treatment. It's quite a low cost. It's suitable for large scale production. As you can see here, we have a belt furnace which 1,000 of parts can be heat treated at the same time, for example. Or here we can use one furnace to place a lot of different shapes in the same heat treatment. So it's this quenching and tempering possible. It can give possible deformations and to the materials. Also, it can be some kind of lack of hardening homogeneity because of depending on the hardenability of the material. Not all materials can be hardened until the core. Some of them has exact composition to increase the hardenability. It means the depth at which quenching can affect. So this has to be taken into account. Also, we have to be very cautious because all the properties that we want to modify with quenching and tempering are limited to mechanical ones. So we cannot improve, except some exceptions, we cannot improve clearly, dramatically the corrosion resistance or the wear resistance by these quenching tempering processes. What materials can be treated? I mean, carbon steels with medium and high carbon content, martensitic stainless steels, some cast irons, and aluminum and titanium alloys by aging effects of the aging processes. Nitriding and case hardening, these surface treatment are also taken in furnaces or in ovens like those here. There are different nitriding methods using gas, salt, or ionic, and also with carburizing. With case hardening, we have nitrocarburizing and other kinds of case hardening processes. I would say they are quite low cost processes. They are ideal for medium and large production because we can, depending on the size of the furnace or the oven, a lot of parts can be on it. it's the possible deformation of the part, since all these processes are done at 500 to 600 degrees. So depending on the size and the dimension of the parts, can be some deformation. The hardness depends on the base material. Yes, that's true. There are special steels for nitriding. There are special steels for case hardening. So not all the steels will reach 1,000 beakers, and not all the steels will be suitable for nitriding, for example. So just check with your supplier which steels can be the optimal for that. High hardness and good lubrication properties. Yes, with these surface treatments, the surface is very hard and it has some lubrication properties. So it's very used for gears, for example, keeping the core of the steel in a tough state and just making a hard surface to avoid the wear of the gears. There's an option to mask to protect everything under treatment. So you can, for example, protect this part here of that piece by painting or by some masking to avoid the surface hardening in these areas. Materials that can be nitrided or case hardened, special carbon steels, titanium alloys, stainless steels, and some aluminiums. Well, the next one is welding. Where welding, it's a very, very known technique. I will talk about cladding. So not joining, not welding two parts together, but to weld onto a surface of the part to improve the properties of the part. So it's hard facing when this welding is for wear protection. Cladding is is more or less a generic word for this welding of coatings for protection. And overlay is more or less when we apply a welding layer to protect the base material against corrosion. So hard facing for wear, overlay for corrosion, and cladding is a general term. So this surface modification technologies, electrode, MIG, TIG, submerged arc welding, electron beam welding, are more or less quite cost effective, or not, and depending if it's very special, no? But in general, welding is quite cost effective. It's ideal for low volume production. It's clear that if it's automatized, it also can be for late scale production by robotic welding, for example, or heavy duty submerged arc welding, for example. It can cause severe material deformation. It's clear. All of us know that because the high heat input of the welding into the material, it can deform it a lot apart. Possible defectology: cracks, pores, lack of fusion. I am not saying that all the welds, all the techniques, all the welders are creating defects, but it's a technology that can create defects. Everyone knows that. So we have to take it into account. Wide range of available properties depending on filler metal. Yeah, that's a very important point of welding. There are a lot of hundreds of different consumables to apply on the materials to modify surface and wear properties. So there's plenty to choose. Materials susceptible to clad or to weld or to protect by welding. So steels, stainless steels, some cast irons, aluminum, titanium, copper alloys. Here it's very important in welding, the weldability. We have to take precautions when the base material is not weldable or it's difficult to weld, because there may be some lot of defects, cracks, pores, or bad experience. So the weldability of base material is a critical point to apply welding. Laser cladding. Laser cladding is one technology that we have in-house. We are very known for that in Europe. We were and we are the only company in Spain using laser cladding to repair parts for customers. And we are very active since during 10 years, 12 right now. So we are quite an expert on using that nice technology to repair and to apply interesting coatings into materials. So yeah, it's a welding process. So it's the welding process with minimal heat input. We have a heat input because we have a very localized input of heat due to the use of a laser beam that is focused here in the surface, in the top surface of the material to be clad. And due to that incredibly high power density here, we can move the heat quite fast. So the welding of the cladding is very high, and this is also causing that the heat input at the end in the base material is quite low. So having in mind that we have a very heat input, there are a lot of benefits on that. Virtually not deformation on base material, and also we can achieve some very nice properties due to that fast cooling of the welding material. That the grain is quite fine, so we can achieve maybe 1 or 2 Rockwell C plus that in comparison with overlay made by TIG or by submerged welding. Other things, so it's not possible to weld manually. As you can see here, the optics are quite big and quite heavy, so it has to be done by a robot or by a CNC machine. So it's an automatic process, which is good for one thing. It's very reliable, one layer after the other. It's qualifiable as a normal laser welding process. So we can have a qualification operator, we can have a WPS. So everything can be qualified to ensure a good quality of our claddings. I would say it's ideal for a small production scale, but also depending on the automatization, you can achieve also very high output. The properties, like in a normal welding, depends on the filler material. Here in COMAS, we are using powder. So in powder, we have quite a lot of filler materials to choose, and other people is also using a wire, which is also allowing you to use more or less the same materials that we have in our portfolio. So we can choose different materials to make these coatings, these layers: Inconel, Stellite, tungsten carbide, duplex, titanium, martensitic stainless steel, austenitic stainless steel, and so on. What materials are susceptible to be applied a laser cladding on? So more or less the same as in a conventional welding. So the weldability is very important. I would say the steels, having in mind that depending on the carbon content, it will be more easy to weld or not. Stainless steels, some types of cast irons, titanium. We are repairing titanium shaft for a customer with a titanium laser, with a titanium coating, without doing in vacuum, just in open atmosphere with a special process with a lot of protecting gas. We can make claddings on titanium shafts. So after that nice technology, hard chrome plating. This is a very known technology, a very friend of all of us that we are dealing in this industry. It's a slow process. It's a process that is, I would say, is going to disappear in not many years. in advance because the baths are very pollutant. The chromium 6 bath, the chromium acid, it is very pollutant, and there are a lot of restrictions in Europe to use those baths. So in Europe, at least, this process will disappear soon. This process is an immersion process. It's a low temperature process. It's electrolytic, so it does not cause deformation. Generally, it's quite homogeneous, although some pores and especially cracks may be present, especially in edges or when we want to achieve a thick coating. So it can be a solution, the cheap solution, a fast solution for some applications, but it has been improved. It has been overcome by thermal spray coatings, tungsten carbide. It has been overcome by laser cladding of ultimate, for example, coatings for piston rods in offshore. So it was an ancient technology that has a lot of limitations, but from time to time, some parts still arrive to our workshop with hard chrome plating, and we are replacing by our coatings or by our other more technological advanced solutions. What materials are susceptible for chrome plating? Steel, stainless steels, some types of cast irons, aluminium is challenging to make this plating in aluminium, coppers. It's not recommended for titanium or alloys. Okay. PVD and CVD. PVD stands for physical vapor deposition and CVD for chemical vapor deposition. These two technologies are technologies that are quite advanced. They take place in a reactor or in a chamber, which is under vacuum. That means that we have to work in batch productions. It's ideal for medium to large scales, since here, as you can see, we can place hundreds of small parts into that reactor, and we can perform that coating to all of them at the same time. It's a slow process and requires specialized suppliers because these reactors are is a vacuum process, so it means that it has to be people that knows how to use the vacuum technologies, and well, it has to be specialized suppliers. Possible deformations, because some of these coatings are done or created between 400 and 900 degrees C, so it has to be in mind that depending on the shape and on the deformability of the parts, it can be some bad experience. There are also some low temperature coatings available in recent years, especially diamond-like coatings at 180 degrees, 200 degrees, which gives you extremely high hardness and extremely resistance coatings, but very thin, 3 to 5 microns. Well, we are using these coatings for all the coating tools. This standard procedure to coat tungsten carbide or high-speed steel coating tools by PVD coatings. And what kind of materials are prone to this surface technology? Steels, stainless steels, aluminum, titanium, polymers. Here we have a lot of, right now we have a lot of automotive parts that are not anymore metallic, but polymeric, and also and with a PVD coating on top, giving you a metallic appearance like these pictures. And overall, tungsten carbide. Tungsten carbide is, I would say, the king of the base material for PVD coatings, because these are very, very, very big production in coating tools in these days. Thermal spray coatings. These coatings are also very used in some applications. We have all this technology in-house. For 40 years, we have been the pioneers and the leading of thermal spray coatings in Spain and in the south of Europe. and we are using every day in our 3 booths that we have in our workshop. So it requires a qualified suppliers as we are, because they are not straightforward technologies. There are a lot of parameters that are affecting a coating, and we have to control all of them at the same time. At the end, the definition of thermal spray is like painting. It's like painting with a gun. It's like painting with a stream of semi-molten particles. So at the end, you have a gun in which it will come some energy, some gas energy, like this flame, or an electric arc, or a plasma arc, to melt the spray material that comes in, the filler material that comes in. It can come in a shape of powder or wire. And then there is an atomization and a propulsion of these molten particles to the substrate. There is one audience that is asking me if we can use PVD coatings in small control valves. Yes, we have some customers, we have some projects with some customers to use PVD, extremely hard and wear-resistant coatings, PVD coatings for control valves. Yes, it's possible, and we are already doing that. Okay, let's continue. So yes, at the end is like a lot of particles that are going to be deposited into this surface. It's like painting, but with metallic or ceramic particles. So it's a cold technique. Why we call it cold? Because there's no diffusion, there's no welding, there's no fusion of the base material. It's like the fusion takes place here in the gun, or here in the gun, but not in the surface. So the heat input to the part itself is quite low. That is allowing us to apply coatings, extremely hard coatings, in a very slick parts like this compressor shaft. Another questions? Okay. No. We can choose, we can apply different coatings depending on the application, because we can use different filler of powders, feedstock power. We have ceramics, we have polymers, we have alloys to apply. So there are a lot of possibilities to use for these coatings. The thickness is in a range of 0.1 to 2 millimeters, more or less. In some special cases, we can go up to 3 millimeters, but it's not the standard way. The standard way, I would say, is from 0.1 to 0.5. With these technologies, with all these techniques, it's possible to perform on-site repairs, on-site coatings, and also inner coatings, as in the picture that we have set in the first page, in the first slides. It was the spraying of the inner surface of a compressor sleeve with tungsten carbide coating. So there is also the possibility to tune the coating properties by modifying the parameters of the process. There are some questions. Okay, no. So you can modify the porosity, for example, of the coatings by modifying the parameters. You can, for example, use a zirconium oxide coating in a very porous way as a thermal barrier coating, or you can use it very dense and very with a low porosity to protect some paths for a molten metal. So, for example, zirconium oxide can be used in the same material, zirconium oxide, but with two different coating properties for two very different thermal final applications. One good thing, clear advantage of the thermal spray coatings is that we can apply all these coatings virtually to all surfaces. So all base materials can be protected by thermal spray coatings. As we are not welding, the weldability is not an important key for thermal spray coatings, but we can implement a coating onto copper, titanium, steel, glass, ceramics, carbon fibers, and so on. Very interesting applications. And final, we are lot of other technologies like electroless nickel, which is very used today for food application, protecting coatings, nickel PTFE, still using some plating. We use some silver coatings by applied by plating to protect some reactor joints and to protect them for the galling after once they are installed in the reactor. With the lid, with the cover, they press a lot to seal the reactor, and this metallic ring is pressed into between two metallic surfaces, and this silver coating inhibits the galling between all the surfaces. Cadmium, which is not anymore allowed in Europe. Other people ask for zinc coatings, galvanizing. In the aluminum and titanium parts, we can do anodizing, which is an electrolytic process which creates a hard and thin protective coating into the surface of titanium and aluminum. Shot pinning is a very interesting technology to modify the tensile properties, the residual stress in the surface. This is a technology that it's based on the shot in the impingement on this shot called particles to the surface, and the surface gets a compression residual stress that is delaying the appearance of fatigue stresses. So it's a technology that is very used in aeronautic applications. Painting, coatings, and epoxies like Loctite or Belzona are very used in pumps and in other oil and gas applications to protect parts for corrosion and wear. Also cold forming, like lamination. We use lamination for the compressor rods, reciprocation compressor rods to fabricate the threads. These threads are not machined in the lathe. They are cold formed. They are laminated to create here a compressive layer, a compressive residual stress here in the bottom of the thread, to delay, to avoid the appearance of fatigue cracks in the thread. So at the end, and as a summary of all these surface modification technologies, I have made a silly or a very simple table which correlate hardness and thickness. And you will realize quickly that if we want about 500 beakers and 0.5 millimeter thickness layer, there are plenty of technologies that will be suitable for that layer. But on the other hand, if we want, for example, 2.5 millimeter laser cladding or layer with 1,000 beakers, it can only be applied, for example, by laser or by welding, depending on the stresses, or here in this case, extremely thin coatings, but extremely hard only applicable by PVDs, for example. Thermal spray here, it has a very big range of thickness and hardness, the same as laser or welding. Okay. So with this nice slide, we are at the end of the presentation. So conclusions. Some questions. Can you apply a laser cladding coating onto titanium-based material? Yes, I have already said during my presentation. We are currently applying a laser titanium layers onto a titanium shafts that are that has lost some dimension. So we are using a titanium cladding to recover the original dimension. Another question is, the thermal spray is the best? Well, I would not say it's the best. I would say it's one family of technologies to use, one family of technologies to choose. It's complementary. They are complementary with laser, with PVDs, with other techniques. There is no one universal technique. There are a lot of techniques to use, depending on each application, each part, each customer. So I cannot say that thermal spray is the best. It's one of the tools that we have. So let's continue with the conclusions. So there are many technologies that can improve surface characteristics of the parts. It's fundamental a close communication with the end user to understand their needs and the expected outcome. Sometimes it's necessary to tell the customer that he might be looking for impossible things, and it's not always nice to tell the customers that. It's necessary to know thicknesses, hardness ranges, part general dimensions and tolerances to check if the parts can fit in chambers, furnaces, reactors, booths, workshops, or it has to be on site or whatever, in order to avoid incompatibilities or inherent to applications. Last but not least, we are proud to share our broad experience repairing unique parts and make ourselves available for our clients, advising them the most suitable solutions and techniques to meet their needs. So, another question, what about cobalt or nickel-based hard-facing laser clad onto titanium-based material? Is this common? Well, frankly speaking, titanium is hard to clad because as laser cladding is a welding technology, it's a diffusion technology. Depending on the compounds, on the mixture between cobalt and titanium and nickel titanium, it can be impossible or not. If I had to choose, I would choose nickel, because nickel titanium is a material, so maybe the compatibility of nickel and titanium are higher than cobalt and titanium. I would say no, it's not common. I know that for titanium shafts, there is people that is using thermal spray coatings to repair or to increase the wear application or the wear properties of titanium-based spare parts, especially in aeronautics. But by laser cladding, we haven't tried. We have tried titanium over titanium, but not nickel or cobalt. Okay. So it's time for questions. I'm open right now for discussions. If someone wants to make a question by speaking or by just writing something in the chat, or anyway anywhere you want, to my email address, I will be available for you. Thank you for your time. I hope that you have enjoyed everything, and I'll see you soon.
Hello. Hi, Jaume. Hi. I would like to first of all thank you for this amazing presentation. I personally find you a great teacher, that you teach me every day something new, and I think that in this presentation we saw a lot of interesting information about surface treatment. And well, as you said, we have a few minutes for some last questions. I think that at the moment you have answered everything. And in the meanwhile, I would like to say that everyone who has attended, if you would like to contact our sales team, we are always available. We have Tarek Murad for the Middle East. We have our contact Hakim for Algeria, and myself for the European market, or anyone who would like to know more. And well, I would also like to add that in this lockdown, we are taking some time to arrange more webinars. So this is all thanks to you, to the people who are watching. I hope that very soon we can arrange another one because we are seeing that they are quite a success. And well, nothing more to add. I would like to thank everyone for assisting, thank everyone for listening and for participating. And well, if there are no more questions, we would like to close this webinar of today. Okay, Jaume?
Yes, it's fine for me. By the moment, there's no more questions, so yeah, it's the right time to say goodbye. Stay safe, stay home, and
Stay safe.
And good luck.